So in this video we go into a little more detail on exactly how Spanning Tree works. And Spanning Tree, for being one of those topics that you generally don't have to mess with and you generally don't have to configure, you sure can get into a lot of detail, and hopefully I won't bore you too much with all of that lovely detail. So when it comes down to it, Spanning Tree is pretty much all about the root bridge and the best path to that root bridge. The root bridge is pretty much exactly what it sounds like. It is the bridge or switch at the middle of your network, and that root bridge has all of the traffic pass through it. If it's going between two switches that are not directly connected, it's going to go through the root bridge at one point or another. You can see why you want to manipulate which switch becomes the root bridge just from that very basic definition, but we'll get more into detail in that here in just a moment. Now, all the switches on a LAN or a VLAN elect the root bridge. This way, all of the switches in a LAN or a VLAN are in the same spanning tree, and they all agree on who the root bridge is. And that way, there's no confusion anywhere along the line. And again, this all happens at layer 2, so you don't have to worry about the switches being on trunk ports like you do with VTP, or being in the same layer 3 network like you do with routing protocols. This all happens, again, pretty much automatically, but you do want to manipulate how it works. The root bridge is elected using the bridge ID. The bridge ID is an 8-byte identifier. The first 2 bytes of the bridge ID are the priority. The priority on every switch defaults to 32,768, or right in the middle of that 2-byte range. The other 6 bytes are the system ID. 99.99999 times out of 100, it is the MAC address of the switch. If you look at any switch, you see the system MAC address. On some older switches, it's referred to as the BIA or the burned-in address. And that's the system ID part of the bridge ID in Spanning Tree. Now, unless you tune the bridge priority, the default parameters, which every switch has the same priority and every switch uses its MAC address as the system ID, all of that means the switch with the lowest MAC address will become the root bridge. Now, if you go look at some of your hardware, and you'll see this when we get into our lab, because MAC addresses are assigned sequentially by most manufacturers, this generally means that the oldest switch in your network by default will become the root of Spanning Tree. Now think about that for a second, let it sink in. If you have a large network with, say, 50 switches on it, go find the absolute oldest switch on the network, and that is most likely the one that all of the inter-switch traffic is going through. That's kind of a scary thought, isn't it? And that's why I go back to my statement that you always want to engineer which switch is the root of Spanning Tree, because you don't necessarily want your oldest switch being the root of Spanning Tree, because you run into bandwidth problems and CPU problems. Plus, the traffic can take unexpected paths through your network, and a single link failing can take down your entire network because it breaks the Spanning Tree in half. Now, you'll see when we get in the lab, and we'll also talk about this a little later, that each VLAN can have its own Spanning Tree. So each VLAN could have its own root. So if you have a redundant pair of switches at the root of your network, switch A could be the root for VLANs 10, 20, and 30, and switch B could be the root for VLANs 40, 50, and 60. And we'll get into all that later on. Another reason why you want to engineer how Spanning Tree works is if you leave all of your switch priorities at default, Spanning Tree can reconverge with unexpected results when you add a switch to the network. This actually happened at a job that I worked here just recently. We were doing some network maintenance overnight, and a department had a switch that they were wanting to add to the network. So they didn't tune any of the Spanning Tree parameters on there. They just plugged it into the network. Since this switch was older than the current root bridge in Spanning Tree, the entire Spanning Tree reconverged to where that switch was the root of Spanning Tree for all of the VLANs. That switch was older than the Nexus switches at the core of the network, and it brought the entire core network to a screeching halt because that switch could not handle all of the traffic between all the different VLANs in the core of our network. So you can kind of see that Spanning Tree is like bacteria. When it's good, it's really good. When it's bad, it's horrible. So that's the great overarching view of Spanning Tree. Let's get a little bit into exactly how Spanning Tree works at the nuts and bolts level, because again, that's what we do here in the ICND2 exam prep. Spanning Tree has 2 basic port types. we have the root port, and that is the port on the switch that is closest to the root bridge. And again, I've got a network diagram here in just a little bit. It'll make a lot more sense. The designated port is the port on a specific network segment that is responsible for forwarding Ethernet frames on that segment. So you might ask yourself, well, in a network where everything's connected to everything else at some level, how do you know which one's a root port, which one's a designated port, and so on and so forth? Quite simply, the root port and designated ports are determined by the port cost. Each port in Spanning Tree has a cost associated with it, the cost to the root, and that cost is determined by the bandwidth of all of the links between that port and the root bridge. And here's a little table that's got some of the interface bandwidth and the resulting Spanning Tree port costs. Again, you can get this information from Spanning Tree, from the Switch OS, if you do the show Spanning Tree command, which we will do in our lab. And you don't have to memorize this table, but as you can see, the faster the bandwidth, the lower the cost. So let's say you have two switches that are connected to each other, and they're connected with redundant links. One's a 1 gigabit link and one's a 10 gigabit link. Well, Spanning Tree will pick that 10 gigabit link because the Spanning Tree port cost is lower for 10 gigabit versus 1 gigabit. We'll pause here and pick up our discussion of Spanning Tree in the next video.